the recording. And we should be good to go. I'll wait just an extra minute or two just in case, but if not, it's not a big deal. Makes it a little easier on me anyways. I don't have to worry about talking with a bunch of people. Alright, well, let's go ahead and get started. Recording's going. Can you guys see my screen? Fine.
Yeah, I can see everything.
Alright. So, radiation. Gonna be going over what exactly radiation is, some of the ways that we calculate our dosage, and different quantities, and difference between like the US and SI units for it. A little introductory effects on matter, because that's a big component, especially in these reactors. Knowing how things are going to radiate, what's going to do, the effects, how often we have to replace it, all that good stuff. Then we're going to get into a fun little tool called SRIM, or TRIM, if you guys have ever heard of that. And then just go into questions and, you know, everyone's favorite slide references. So, first, just a little introduction of what radiation is exactly, because everyone seems to hear that and go running away. So there's two main types. We have nuclear radiation and electromagnetic radiation. They are different, but the main topic of this one's going to be nuclear radiation. It's putting a few little things on electromagnetic so that people are aware that it's a thing. And part of nuclear is electromagnetic. Electromagnetic is what we're a little more used to. It's what light is, what heat is going to be, the radio waves, all that good stuff. And those are made through oscillations of electric and magnetic fields going through space. So basically, electric fields make magnetic fields, make electric fields, make magnetic fields. And you have this continuation that is only slowed down by the permeability of real space. And that permeability is what the speed of light is. So anytime we're talking about electromagnetic radiation, it's going at the speed of light. It's what a photon is. It's what anything you see is. But that's why we know the exact value of the speed of light. The maximum in a vacuum is because it's only affected by two factors: permeability of the electrical and magnetic fields going through. I mean, obviously, speed of light is calculated for a void with no interactions. It can change in different mediums, such as water. You guys ever seen that nice little blue glow in a nuclear facility? That's electrons going faster than speed of light because they can move quicker in that medium of water, but in just air or void, nothing's gonna move faster than that. So nuclear is going to be any kind of matter or energy emitting from a nucleus. We have a little diagram down there showing a few of them. We're not going to talk about all these. Mostly gamma, alpha, beta. Those are the ones everyone mostly knows. And another thing is that there are two different types of radiation. There's ionizing, non-ionizing. Non-ionizing is the safer kind. It's going to make up most of the electromagnetic spectrum. Ionizing pretty much all nuclear is going to be ionizing, and high energy electromagnetic is going to be ionizing as well. And what that basically means is that it's going to be affecting the electrons on atoms. It's going to be ionizing them. That's where the term ion comes from. It's because it has a different electron amount than their stable form. So ionizing, bad, because we're stripping off electrons, going to change properties, going to try to form into other things. That's where a lot of the damage comes from. And then there's also neutral and charged radiation in the ionizing category. The neutral is going to be any kind of electromagnetic because there is no charge. It's just energy. Electromagnetic energy or electromagnetic radiation is just energy moving through space. It's going to interact with stuff. If it's going to change anything, that depends on the energy of it. But there's also charged ionizing radiation, which is like alpha, beta, and we know that electrons are going to be negatively charged, and alpha is going to be positively. We'll get to that a little more later, but it's just a little introductory. Just electromagnetic, nuclear. Like I said, mostly focusing on nuclear here. Just a little more on electromagnetic. I'm sure you guys have seen this, or a graph like this before, where you have radio, microwave, infrared, but I never really understood it until I kind of understood radiation itself a little better, because there really isn't much, like, it seems a lot more complicated than it is, because you have like all these different categories, all these different ways to categorize it. Why is this one visible? All that kind of stuff. But all this is energy is a function of frequency. H is Planck's constant. This is nu. It's not actually a V. It's nu for frequency. So the higher the frequency is, the more energy we're going to have. There's nothing else to that. It's just the faster the oscillations of our electric and magnetic fields are, the more energy these are going to possess and be able to transfer into whatever they're interacting with. So, yeah, obviously a lot of these are non-ionizing. The ionizing threshold is right about here. Can you guys see my mouse on this? I think you should be able to from my screen, right? Well,
Yeah, I can.
okay. So the cutoff is right into ultraviolet. You can have ultraviolet that is ionizing, but mostly whenever you're talking about ionizing, gonna be talking about X-rays and gamma rays. Obviously, if you go get an X-ray, you're going to be getting dosage. It's not always great. It's not a very high dosage, but it's dosage. And that's why you have to wear, I don't know if you guys have ever had to wear like the metal blankets and stuff for materials that or for areas that you're not actually X-raying. It's just to prevent that extra ionization, because ionization is never really a good thing. You want to try to avoid it when possible. I mean, just a little controversy to that, but that's not really today's topic. But yeah, basically, we see in this little area, which is kind of important for some facilities, such as scintillators, which we'll get into a little later. So basically, if the electromagnetic radiation is this frequency, we can see it, just because of the way that we are developed. But there's a whole other range. But at the same time, microwaves aren't going to kill you because they're not even ionizing. They're really low on the energy spectrum, even less than the light that we see. So, moving on to a little more nuclear radiation. So, why do these nuclei radiate? And it has to go down, I touched on it last time, a little bit on stability. Atoms want to be in their most stable configuration. They want to be in their lowest energy state. So what this means is that they're going to do whatever they can to reach that state. Here we have the isotopes that we know of, and you see such a small percent of them are actually stable. Obviously, this is not what is all around us. It's not just stable stuff around us. We have all of this to worry about. It's not labeled for sake of actually fitting everything on here, but you can see our neutrons, protons, so we're going to have like hydrogen here, and then, uranium somewhere around 230, 92, somewhere around here. There's no like stable isotopes of uranium. Thorium's going to be up here too. Any other elements, just follow the proton amount. They'll be up here. The other thing is, you can see it's not linear, the way that elements grow. Because if it was, it would be following this line all the way up. And this is due to more neutrons being needed to hold our configurations together. Because when you think about it, protons are all positively charged in the center, right? So they're always going to be pushing away other protons. So you need that glue of neutrons to keep everything together. So as you're adding more protons, you need more and more neutrons to help. And that leads to stability issues, which means that the further we go, the less stable isotopes we're going to have until we just don't have any after a certain point. So how do they reach these stable spaces? Well, they get rid of stuff. Obviously, they could absorb stuff if it was around, but you don't always have extra stuff to just absorb to make it neutral. And that's kind of the point of, on the periodic table, you've probably learned about elements that want to gain electrons, elements that want to lose electrons. It's that kind of idea. So we're going to be trying to remove stuff, such as electrons, even just neutrons, try to get more stable configurations. If it gets heavier, you're just going to flat out shoot helium atoms out, which is what we know as alpha particles. Anything to get to this lower base, or its lower energy state. So that's why things are going to be radioactive. And these are referred to as disintegrations. Whenever an atom is transmuting like that and giving off something. So that's basically why we have this nuclear radiation. It's just stuff constantly trying to get into a state. And the more radioactive it is and the more that it wants to change, the shorter its half-life is going to be. Because half-life is going to be referring to how quickly we're getting rid of that stuff. Something like uranium, or you have it in the billions of years for its half-life. Like, yeah, it's not stable, but it's not trying to, get down there in a crazy quick method. But other isotopes, which are very, very unstable, I mean, they have millisecond half-lives. Like, they're gone. They can't be in that configuration. And so what this also means is that the lower the half-life is, the more radioactive it is, the more stuff you're going to get from it. So whenever people say like, oh, it's radioactive, okay, what's the half-life? If it's 3 billion years and it's, emitting one beta particle every 100 days, who cares? So that's something to keep in mind when people say radioactive, because half-life does matter. So yeah, everyone has heard alpha, beta, gamma. They sound complicated. They're not. Alpha, helium atom, 2 protons, 2 neutrons. Beta, electron. Gamma, photon. They're going to have different mean free path. I don't know if you guys ever heard that, but how far they can go into certain materials depend a lot on their mass. Alphas are the most massive. They're going to be stopped by paper. They're going to be stopped by your skin. They're not going to go very far. They're going to be interacting with stuff, and since they're so heavy, they're going to be constantly hitting all these particles in the air and slowing down until it doesn't matter anymore. So if you have an alpha source outside, it's not going to do a lot to you. Inside's another issue. We'll get to that. Electrons, a lot less massive, about 1,000 times less massive than a proton or a neutron. So they can go a little further, but still not really penetrating. They'll get a few millimeters into your skin, but nothing too crazy. They will affect you more from an outside source than alpha. So photons are just light. They're just electromagnetic radiation. It's just going to shoot right through you. You're not stopping a photon, which can be both a good thing and a bad thing. Because if it's just going to shoot through you, it's not going to be interacting as much as these other ones if they were inside of you. But at the same time, it's a lot harder to stop these things. You're going to need big lead shielding areas or other dense material to try to beef up the interactions. But these two don't need nearly as much protecting. There's actually a very famous paper. It's more of just a fun fact than anything, called the alpha beta gamma paper. It's written by Alpher, Beta, and Gamow. I think it was Beta. Didn't actually have anything to do with this paper, but Alpher had a student named Gamow, and he was like, it'd be funny. Let's just throw Beta in there. So this person didn't write anything on it, but it's still called the alpha beta gamma paper. It's not super relevant to today's topic, but it's still interesting because they were doing the origin of chemical elements and their abundances from the Big Bang. Doing these processes, we can determine, hey, how did all these materials fuse and interact in the first seconds of the Big Bang? I mean, the first 20 seconds basically set up our entire composition of the universe. And they came up with this wonderful plot, which has been tested to be pretty accurate on the abundances. There's some interesting things to take away from this plot based on stability. Like, we know that iron very stable, so you're going to have more of it. And then other things like beryllium are going to be really low on here. It's an interesting read if you're interested in our composition. Obviously, there's a lot of hydrogen and helium. We don't have as much on Earth because it got swept away. The outer planets kind of nabbed all of our hydrogen and helium, but that's fine, I guess. They can have it. So, yeah, that's some basics on radiation. If you guys have any questions, just type it in chat. I know most of that was kind of a little more basic stuff, but let me know. So on to some dose measurements. So how do we measure this stuff? And that's a very tricky question because there are a lot of units with this stuff, and I still don't have them all memorized to a T on their exact definitions and everything. But I'll try my best to give a general rundown of it. So the most basic unit is the activity, or radioactivity. These are going to be in becquerels or curies. Curies are the US unit, and becquerels are the international. Becquerels are pretty intuitive. It's just 1 disintegration per second. We have one atom doing something per second. Not a crazy concept. Now, a curie is still disintegrations per second, but instead of 1, we have 3.7 times 10 to the 10th power. So, a very large amount. It's a very big number. You're usually not going to measure stuff. Yeah, America. Usually not going to measure stuff in straight curies. If you are, you probably shouldn't be there. This was after Madame Curie. It was actually named after her late husband, and it is 1 gram of radium, I believe. I think radium. I always mix up radium and radium. I'm pretty sure this is radium. So 1 gram of radium has this activity. And they tried telling her, hey, that's really high. Maybe a milligram of radium instead. He's like, no, this is for my husband. He was larger than life. We got to give him a whole gram. So that's how we have this stupidly large unit for measuring radioactivity now. And then we have exposure. The international is coulombs per kilogram. So if you're talking about air, if you have like 4 coulombs of charge per kilogram of the air, that's your exposure rate. There's also Rankine, which is the US version. It's a little weird. I don't remember the exact numbers on it because it's like 0.06 something. I don't know. Either way, that's charge to air. Not super important. We don't measure a lot of stuff with it. There's also Kerma, which is related to dose. It's the kinetic energy of radiation absorbed per unit mass. And the Kerma comes from the kinetic energy radiation and MA from mass. I don't know. I don't write these units. But that's the kinetic energy that we're getting. And it's similar to dose, but it's going to overestimate it at large amounts. So we don't use it that much. It's fine for low doses, but usually you just go with absorbed dose, which we're going to be measuring in gray or rad. Gray is the SI, rad is the US. 1 gray is 1 joule per kilogram of mass, which doesn't sound like a lot, like 1 joule, but 5 gray is enough to kill you, depending on the other factors. And then the US, it's just 100 rads. I don't know why we had to change it. 100 rads, 1 gray, but that's how we measure it. So this is what is actually being absorbed into your material. So if you're absorbing, 1 joule per kilogram of beta radiation, you got 1 gray. And then last we have effective dose, which is how we will measure the amount that you're getting as a person, because these are taking into consideration the weighting factors of radiation and what part of your body is getting that radiation. So this is the most important one to know, because an amount of alphas and an amount of gammas are not equal. If you get this amount of radiation just on your skin or in your bones, it's not equal. One, you could have a little vomiting and be fine. The other one, you could die. So these are very important. Sievert and Rim. And it's just a straight. So you go from gray times your weighting factor times your radiation, or times your body part, and you get your Sievert or Rim. And it's the same conversion of 100 Rim is 1 Sievert. And you're usually not going to measure things in straight Sieverts. Just like the Curie, it's usually going to be in millisieverts, millirim, that kind of stuff. So 5 Sieverts is a D50, which means that 50% of people will die if you absorb 5 Sieverts all at once. So it doesn't take a whole lot. That's why I said we usually measure things as millisieverts for like your annual considerations and that kind of stuff. And anytime you see like a D50 or D75, it's death for 50% or death for 75%. So just, some people can get a low dose and die. Other people can get 20 sieverts and walk it off. There's no real way of knowing. Has a lot of factors. And there's also acute and chronic ways to absorb radiation. Acute is all at once, just getting hit by this blast of radiation, like the Demon Core. They just got a very acute dose. They got hit by all this radiation at once. And that's going to be a lot more deadly than chronic. Chronic is over time. If you're living in a place with higher background radiation, that's going to be considered a chronic dose. You're getting this dose over months, years, days, and your body's going to have a lot more time to accommodate and repair for that. So you can recover a lot better from chronic versus acute. So there are a lot of different ways that we detect radiation. There's solid state detectors, gas field detectors, scintillators, Geiger-Muellers. They have their different applications. Something like a scintillator or a superconductor detector, we're not going to be using in like nuclear reactors because they can suffer a lot more damage. Meanwhile, stuff like the GM counter and ionization chambers can kind of withstand a lot more abuse before having any kind of defects. So there's not one fits all detector type. Like for the MSTR reactor on my campus, we use ionization chambers and the GM counter for the most part. So gas field detectors, and those are gonna basically be getting the charge out of the air and interacting with a piece in the center to give you a amount of radiation that's interacting with it. But I'm not gonna go too much into these because there's a lot to them. But I will say scintillators are cool. They are going off the basis of, wow, scintillation, which is radiation interacting with something and visible light being emitted, which was always interesting to me because you're basically having these interactions that are going to be producing electromagnetic radiation that is just so happen in the visible wavelength. So we can actually see these interactions taking place. But like I said, they're not very practical. There's a neat concept if you guys want to look into anything like that. So this is some radiation weighting factors. A lot of it has to do with mass. If an alpha particle is going to be hitting you internally, it's going to do a lot more damage than a photon. Photon, gamma, same thing. Well, not really. A gamma means that it was emitted from the nucleus, but it's a photon. And photons weren't from a nucleus. So if it doesn't have a lot of mass, it's just going to have that one weighting factor. Electrons don't have a lot of mass, has one. Neutrons, they change based on energy. They can get up to alphas. Protons are kind of middle at 5, along with low energy neutrons. In nuclear reactors, you can have up to 2 to 20 MeV neutrons being produced right in the center of it, but you're probably not going to stand in the center of a nuclear reactor. If you are, you probably have bigger issues. So in these values, you can look up a million graphs and charts, and you're going to get a different value every time. They're not set in stone. It's kind of about interpretation. But just know that heavier ones are going to have bigger weighting factors than stuff like a gamma. Same thing with body parts. You do have different weights. So basically, if your entire body was 1, you have different compositions of what matters. And a lot of this has to do directly with the new cells that are being produced there. If you have more cells being produced, it's going to matter more. A place like your bone marrow, where you're constantly producing these new cells, or in your gonads, it's going to affect it a lot more because you have more generations of cells that are going to be affected. And like I said, with the weighting factors, these will change. Some have gonads as 0.2, some have it as 0.8. It really just matters on who you're looking took the data. So take these with a grain of salt, but it's more about just knowing different tissues are going to have different weighting factors. What this also means is that if you're having radiation over your whole body, that's the worst, because that's going to be a weighting factor of 1. Like I was saying with like the grays and stuff. So if you had 1 gray of alpha particles into your breast tissue, then you just take the 1 gray times 20 times 0.12 and you get your sievert dosage. So it's not too crazy on how to calculate those. And then with these dosages, there's also different D50s and D thresholds. The threshold is going to be like the minimum amount before you start seeing significant results. You can see stuff like your eyes are pretty low, your testes are pretty low, a lot lower than like your skin. So you can get straight death if your bone marrow gets a certain amount of radiation. Yeah, like I said, D50 is a percent of 50% of people are gonna die, and then this is your threshold. This is based off 0.5 grays an hour. But like I said, numbers with a grain of salt. If you look them up, they're going to be different somewhere else. So why do we care about these like bone marrow calculations and everything? Why is that kind of common? Well, it's because our body will take N isotopes because they don't know it's bad. They just see something like cesium, and it's very chemically similar to potassium. So they put it where potassium goes. And that's not really a good thing, because then you have all these places in your body where you just have this radioactive cesium going around. Specifically with like strontium, calcium, that's going straight to your bones. That's when these bone marrow calculations get important, knowing how it's going to affect you there. And you can get all kinds of ways to uptake this strontium. If there was some kind of nuclear incident or fallout, and it gets into the groundwater, if it gets into like feed for cows, their milk becomes contaminated, and you have the strontium in your body now that's going to sit there for however long, constantly giving you radiation. So it's pretty important to know how these are going to get out into the environment and which areas are going to be affected. Because if you don't look at little things like that, I mean, a lot of people can die. And we have some of the critical organs over here. Strontium is bone, iodine, thyroid, radium, bone, uranium, kidney, plutonium, bone. So a lot of bone stuff. Thyroid cancer is probably the most common that you can run into from radiation. Luckily, it is one of the easiest cancers to deal with. But in instances like Chernobyl, a lot of people died from thyroid cancer, specifically from this iodine 131 being released into the atmosphere. We don't have exact numbers, depends on who you ask, but it definitely had an impact. And that's why, if you guys have ever heard of iodine tablets, it's specifically for iodine 131. You take these iodine tablets so that your thyroid uptakes it, meaning that you won't uptake this radioisotope, because your body doesn't know the difference. It just knows, hey, I have enough iodine. I don't need this other one, so I'm not going to absorb it. So if you can get that out of your system, it can be great. But with that, there are medical applications to stuff like this. If you have hyperthyroidism, you can actually take low doses of iodine 131. It'll be uptaken into your thyroid, destroy some of the overactive glands, get out of your body in, say about 90 days. I think it has a half-life about 9 days in your body. There's a biological half-life for all of these, and it's different than a regular half-life because you're going to emit it from your body in different ways. So that's something to consider too. is that it's not always just stuck in your body, but you have a whole nother system of half-lives called biological half-lives to worry about. So there are medical applications to some of these radioisotopes, but it has its limitations because obviously if you take too much, you can end up with hypothyroidism, where your thyroid isn't active enough. But uh, that's why we need to know all the numbers so that we can help people. And it's another thing with this is the long-lived ones are going to be a lot more dangerous because, like I was saying, they can seep into your groundwater. They can get stuck onto feed for animals. They can just linger around and be really annoying and persistent. Here we have a Russian defector named Alexander. I'm not going to try to pronounce that. And you guys might have heard this story. It wasn't too terribly long ago. It was a big news story too, and I think the UK, where he was poisoned by polonium 210. So what is polonium? It's an alpha emitter. They basically snuck it into, I think, his drink. He drank it, and so yeah, he has this alpha emitter sitting in his stomach. And what that's gonna do is just tear apart his digestive system. It's going to break off every mechanism he has for absorbing nutrients, and he basically just starved to death because he can't uptake anything. So he gets this acute radiation sickness, and he can't. It doesn't matter how much he eats; he's not going to get any nutrients, so he dies. Um, and yeah, obviously the Russian government had a play in this, but just an interesting way to deal with someone, I suppose, by just showing how dangerous these things can be. But what's the? I just threw in a little thorium slide here because by knowing thorium, a lot of people really love it. And this is one benefit I will give to it, is that it does emit these strong gamma emitters from its decay chain. Don't worry about all these, just worry about the red arrows. Bismuth and thallium. Um, they are going to be emitting a lot of gammas, which makes it really hard to deal with. So obviously, you can't just go snag this stuff after it's been irradiated because you're just going to die from gamma rays. So it does make it more of a hassle to have reactors for because you require more shielding to deal with these as it's irradiating in a reactor. But at the same time, it's harder to steal and to work with to filter out some of the things like uranium 233, or I mean uranium 232 and other isotopes that they would want to get their hands on. So that's one benefit to thorium. And the last thing was talk about LARA. It's kind of the golden standard of nuclear safety. I'm sure everyone's probably heard this before. As low as reasonably achievable. What does that mean? It means if we can avoid radiation, we're going to. If we can minimize the amount we're going to get, we need to do that. But it doesn't mean you have to have a giant lead shield around everything. It's just getting it as low as you can without going to extremes. The three main factors in that are time, distance, shielding. The easiest one of those to utilize is distance. Obviously, they all matter a lot, but whenever you think of a source, you have to consider that it's emitting everywhere. So by just taking a few steps away from it, you can minimize your exposure by a lot. The distance follows an inverse square law, meaning it's a 1 over distance squared term. So if you're at 2 meters, it's 1 over 4. If you're at 4 meters, it's 1 over 16. And that can really make a difference on the amount of exposure that you're getting. Like our source on campus is a cesium-137 source, I believe. And if you were standing 2 meters from it, you would be fine for months before you even reach your annual dosage. I mean, completely safe. You'd be like 4 months before you can get an annual dosage, which doesn't even mean you're going to have any effects. That's just the amount that, the government says, hey, this is safe. But if that was 2 centimeters away from you, you'd die in a couple hours. So that's why a lot of radioactive isotopes are handled with things like tongs and basically trying to keep that away from your body as much as possible. Obviously, shielding, the more thick something is, the better it's going to keep everything out. Uh, lead is great. It really just has to do with like the density. Um, water even works. I mean, if you have a reactor going, and that's why during these water pools, it acts as a shield. It's hitting all these radioactive particles and slowing them down until they won't even reach you. And obviously, time. If you have a source, you're not gonna stand there for an hour. Probably do it as quickly as you can and get out of there. But yeah, that's Alara. Very basic golden standard for radiation. And then radiation sucks, but you can't escape it. It's everywhere. It's in the stars, it's in the radon are all around you. It's from gammas from the sun, and it's just no getting away from it. And it really does change on how or where you live. So over here we have millisieverts. I know the graphs are kind of hard to read, and I apologize. I couldn't find any higher quality. There's a millisieverts per year. Uh, and if you live in a place like Finland compared to a place like the UK, it's a pretty drastic difference. Over 3 times the amount of radiation that you're going to be getting just by living somewhere else. So you're always going to be getting radiation. Nothing you can do about it. And there's also something called the banana equivalent dose. And it sounds funny, but it's kind of an easy way for people to conceptualize how radioactive things are. Because admittedly, like, units are not very intuitive and they're pretty hard to understand, especially when you're moving over to these millisieverts, millirem. It gets a little like, okay, when does this actually matter? So banana equivalent dose, you assume that one banana is 1 microsievert or 0.1 millirem. And what this is from is the radioactive potassium in there. I'm sure you guys have all heard bananas are radioactive. Yeah, potassium 40. It's not great, but I mean, it's obviously really low amounts in there. But you're radioactive. You have potassium in you. Just part of life. And so if you were to eat 100 million bananas, you die. Surprise. But there's other ways that you can conceptualize things, like these chest scans are 70,000 bananas, mammograms 20,000, that kind of stuff. You also see like the difference on getting scans because it does matter on your what type of scan you're getting. Chest X-rays aren't going to be as much as like a CT scan, and that kind of stuff. So it does make a difference, and that's why radiation workers have to, if you get an X-ray, the guy goes and hides behind a shielded area. It's because you don't want to be sitting here getting these X-rays, this ionizing radiation every day, because you're going to reach your limit really quickly. Then you have an average daily background dose of 100 bananas. So, pretty high when you think about it. But it also means that small doses of radiation aren't going to kill you. There's the linear no threshold model, which I know Wind isn't a fan of, but it's what a lot of people go off of, just saying no amount of radiation is safe. There is no threshold for a safe amount of radiation. But obviously, not everyone has cancer from radiation, so does its impact matter? at these really low doses? Probably not. It could even be good for you because your body gets used to the cell death. Whenever you have these ionizing molecules that are going to rip apart some DNA, you've got to kill that cell, and it's got to be replaced. So the better your body gets at that, the more radiation it can handle typically. And that's a theory called radiation hormesis of low amounts are going to be healthy for you because it helps your body kind of adapt to these radiation doses. But none of that's proven because we can't irradiate people for science because that's unethical, as they say. But also saying, also depends on what kind of house you're living in, which was something I thought was interesting. Like these stone, brick, concretes, they're going to be more radioactive than other materials. So depending on the house that you're living in, can affect your radiation dosage as well. But there's a lot of factors that come into play for it. So radiation effect on matter. I guess I probably should have changed the word from matter, but basically materials. Just some basic terminology before we get too far into it. We have vacancy, which is going to be an empty spot. So this atom, this is a little story. This blue atom was right here. All right. We had this particle come, and it had enough energy to knock it out of place. So this particle went up here, this particle went up over here, and now we have this empty slot right here. This empty slot is our vacancy. An interstitial is an atom that kind of gets stuck. It's wedged in between its other atoms. It can't move anywhere. It doesn't have enough energy to go somewhere else, so it's just stuck in these little spots, which is a problem because it changes a lot of properties whenever you have these interstitials. It can change the volume of what we have. It can change the thermal properties, thermal conductivity. So it's not a very good thing. We have something called a Frankel pair, which is this pair of vacancy and interstitial atom. Just the combination of them is referred to as Frankel pairs. The knockoff. So this is going to be our knockoff. It's the atom that gets knocked out of place. The threshold energy is going to be, like, obviously these aren't going to move from no energy. You need a certain amount of energy to knock them out of these places. And these are usually on the EV scale. So not too horrendously energetic, but there is a minimum amount that you need before it starts making a difference. And then finally we have DPA, which is displacements per atom. And this is a really important thing to know for specifically like reactors. A lot of places don't have to worry about radiation displacements too much, but if you're having like 10 displacements per atom, meaning that your atoms are moving 10 times in a time frame, the configuration is going to be completely different. So that is an important parameter. This is just some, just trying to teach some of these words before we talk about them a little more. So, like I said, from these knockoffs, you have primary knockoffs and secondary knockoffs. Your primary knockoff is that first atom that gets knocked out. Your secondary is, okay, this atom that we just knocked out of place, it has enough energy to knock off another atom. Which can be even more of an issue because if you keep giving all these atoms energy and displacing them, they're going to knock off more, and you're going to have this entire cascade effect coming, which is an issue. Whenever you have high energy atoms coming in and knocking these out. So yeah, the energy will get transmitted based off the angle that it's hitting and all that good stuff. The secondary knockoffs are still going to reach like up to tens of EVs, assuming you have like KeV, primary scattering particles coming in. And just for reference, room temperature is 0.0253 EVs. EVs are electron volts. It's a unit of energy. that it's kind of like like a joule. You can translate it. It's like 10 to the negative 19, 1.602 times 10 to the negative 19th joules, I believe. But another thing you can do with these EVs is you can directly relate them to Kelvin with something called the Boltzmann constant. So EV per K is the Boltzmann constant. I'm not going to talk too much about this, but just saying you can translate it. And what this basically comes out to is that 10 EV is 100,000 Kelvin. That's hot. That's really hot. I mean, the sun is, what, like 6,000 Kelvin on the surface? That is very, very hot. But to say that this is our temperature isn't exactly accurate because we're not in thermal equilibrium. But just knowing like the amount of energy and temperature that these atoms are going to reach is insane. This is all not like completely proven because you can't just measure temperature, but a lot of people think that these knockoff atoms reach these stupidly high temperatures for very, very brief time. We'll talk about the time frames a little bit, but just know that, I mean, it's crazy. This was something that blew my mind when I first learned it. Is, we have these atoms that are reaching these stupidly high temperatures for brief moments. But I mean, this is happening inside your body. If you have these radiation or you have stuff hitting you, like you have these temperatures in your body. Like I said, it's not exactly accurate to call it temperature since it's not an equilibrium, but you know what I mean. So like I was referring to with these knockoffs is something we call the cascade. They're binary collisions until we don't have enough energy to knock off anything else. So say our threshold energy is 10 EVs and we have a 100 keV particle coming in and knocking them off, you're going to have a lot of secondary knockoff atoms. You're going to give energy to another atom, that's going to give energy to more atoms, and they're going to keep hitting stuff. And that's what's going to give us, on these right, we have one for kinetic energy and one for potential. I mean, you can see we don't have anything. We start hitting, and it just turns into this beautiful cascade of these atoms just hitting each other and thermalizing and reaching. This is our EVs. So it's just a 10k EV. That's not a whole lot of energy to begin with. With reactors, you have these neutrons coming in at MeVs, which is 1,000 keVs for one MeV. It's not uncommon to get 10, 20 MeV. So it's absolutely insane that this is happening. You can see they do. Whenever you make these Frankel pairs, it's going to still have atoms that are going to find these dislocations and reform into them. So not every atom that you hit out is going to create this permanent defect, but it is going to make a difference at the end. You can see here on our starting, we have a perfect lattice. We're not going to have any defects. But at the end, after everything's said and done, there are differences. And this is exactly why we care about the radiation that's happening in these materials, because not everything is going to find a new home to sit in. And there's 4 kind of phases to this whole cascade system. We have the collision phase, which is where everything is just kind of hitting each other. Like I was saying, you're spreading energy around. But you have your thermal spike phase, which is energy spreading into these nearby atoms and is forming a quasi-molten area where everything is basically melting. We have a quenching phase where this quasi-molten volume is going to be recrystallizing and forming back together into a solid, and we're left with our defects. And then we have the annealing phase, which we're basically in equilibrium, like where we started, but these remaining defects are going to be interacting with other areas, which is what really matters, is this annealing. because this is what happens from the microsecond to years phase as these defects building up and interacting with things. It's a little easier to see in this kinetic energy diagram what kind of defects we had left, because this is the same cascade evolution, or in this potential energy, my bad. So you can see we have a lot of defects here and here that are still sticking around after everything's said and done. Here I just have this is a collision cascade into uranium dioxide to kind of help better visualize this. It's turning into 3D for our atom lattices. I think it was a 10 kV. So you can see like all these atoms recombining with other places while also hitting more secondary knockoff atoms that are going to be going other places. And eventually it'll reach that annealing phase of quasi-equilibrium, and we just have these surviving defects that we have to worry about. You also see the time frame here at the bottom. Picoseconds. A pico is 10 to negative 9th, if I'm remembering correctly. I think it is. So this entire thing is happening in less than 10 times 10 to the negative 9th seconds. It's a very, very quick process. So all of this, we don't care about as much for long-term effects. We're not gonna see this happen. This is just what's going on to create stuff that we can't see happen. So yeah, like why do we need to know these DPA calculations and how it's gonna affect our materials? Well, one application is something called the Wigner effect, which I don't know if you guys have ever heard of the wind scale plant fire, but this is what was responsible for that. Is because we didn't have an understanding of the radiation effects that we were having on our materials. Our graphite, since it is our neutron moderator, is obviously going to be exposed to very high fluxes of neutrons and energy. And what this Wigner effect is it's the buildup of these interstitial atoms into this graphite. So remember, those interstitials, they were stuck in between atoms. And what they're left with in that state is they have potential energy. It's kind of like a ball on top of a hill kind of scenario. You guys remember in basic physics or science, you have kinetic and potential energy. If it's somewhere where it can release its energy, it's got that potential. So that's what these interstitials have. And in this wind scale facility, their graphite built up such high amounts of these interstitials and they had so much potential energy that they just combusted. They had so much energy in them that they just caught on fire. And so we had this, one of the worst nuclear accidents that we've ever had was our graphite just catching on fire. It was in 1957. It was over in the Britain's wind scale. And yeah, again, with the whole milk situation, how I was saying, if you have these radioactive elements that are going to be sticking around, it affects your stock, since you're feeding them from the grass and the other crops that are coming out of this. So they got to pour out, 2 million liters of milk because they didn't want that strontium uptake from this disaster. So this is real applicable stuff. And after Chernobyl too, I don't even know how many villages couldn't use their milk, couldn't use their crops, couldn't use this, couldn't use that, just because we have all these isotopes that are sitting in there that our body would uptake and potentially kill us. So it really does matter learning about these effects and what's going to be coming from them. Otherwise, we're going to get spontaneous fires like this. Another thing was kind of like the Wigner effect. Oh, hello, MT. So another thing was these nuclear effects, this thing called the inverse Kirkendall effect, that basically is going to be based around diffusion of atoms. If something diffuses quicker, then it's going to segregate and you're going to lose enrichment in that area. So on the left here, we have our initial compositions of copper and nickel. But on the right, you can see we have holes in our copper. We have these pores of places where copper has diffused out of our system. And that makes a big difference from an alloying point of view. Like if you have these specific alloys in our reactors and we're suddenly not having enough copper in here to prevent corrosion, to prevent embrittlement, to prevent all this stuff, that's bad. So understanding these effects can really make a difference on how often we have to replace our materials, and all other our enrichment levels. Because if you enrich it with more coppers, then you can take into account this effect that's going to be getting rid of some of that enrichment. So it is really important for these reactor applications to avoid a lot of issues that could come down the line. So now we're gonna look at something I find really fun. It's called SRIM, the stopping in range of ions and matter. And yes, I know this is a very lovely home screen. They're clearly graphic designers. And we're also going to be looking at TREM, the transport of ions and matter. So I have that pulled up here, and I was going to show you guys a few things you can do with this program because it's a free download, fun to mess around with, and it kind of helps you look at some stuff if you want to see how some ions are going to be interacting. So you can add what you're shooting. So right now it's a hydrogen. We have our mass, energy, 10 keVs, and you can choose what you're going to be depositing that into. I'm not going to mess around with this too much. I'm just going to do a few of the demos. So we'll start with something called a def ray. So we'll go ahead and see how this looks. What we're doing is we have a hydrogen that we are shooting with 1 giga electron volt of energy straight into air. And we're going to see how far that's going to go. And what this is doing is called a Monte Carlo simulation, which is kind of golden standard for nuclear applications. If you guys ever heard of MCNP, basically any program's going to be dealing with like neutrons and ions and stuff is Monte Carlo. You're just running these simulations again and again so we can get an idea of what's happening. So here's our death ray of the 1 giga electron volt hydrogen. And we can see it's going over 43 kilometers before it stops, which is interesting because that's a very long way to be depositing all this energy. And a lot of people thought before that we could have applications for this in military. You know, if you can just shoot this radiation over at someone 43 kilometers away from you, that's a pretty good advantage. But we have found since then that's not great because you can see this accuracy here isn't the best. We have a lot of factors contributing to where this is going to end up, so we cannot shoot these protons at someone very confidently was how it's going to end up. But yeah, this SRIM is just going to be, so we can see we shot 27 so far, and that's our cascade or our diagram of it. And it's just going to keep going. And you can see other methods of kind of interpreting the data on here. See the ion distribution or ionization as it's going through. So that's a fun little thing to mess around on. Another thing I was gonna show you guys was the thyroid. So this is shooting a hydrogen into a human. We have all of our compositions that are usually making up the body, and we have our skin, adipose, skeletal muscle, our thyroid, and then more skeletal muscle. And what this is going to show is that's not. Hold on. Shouldn't be at 2 meters. Sometimes there's little issues with it. Just try to open it back up. Sometimes the range wants to change on me. We'll go back to trim demos, thyroid. Okay, there we go. This is showing our ability to kind of put this radiation into certain areas in our body. You know, if we've got cancer cells or a tumor or other things that we want to be depositing our radiation in, you can do that. So this is a 27 millimeter scale, and you can see how accurately we can get this radiation in there without suffering into the other areas. These are, I mean, they're fairly accurate, but they are going off some assumptions. These are a kitchen peas model, which basically means that we're assuming everything is a hard sphere, which isn't entirely accurate for collisions, but it's still an easy way to kind of visualize how these ions are going to interact. And this is what a lot of cancer treatment's trying to do right now is, you know, these proton accelerators for medical applications. This is exactly what it is. We can shoot these into these areas that we want, and it's not going to do too much more damage than what we want. Obviously, there's a stray every now and then, and you can get a few things that might end up. I haven't seen one actually end up in skeletal muscle, but I've seen it end up pretty close from these. So there is a lot of variability in it, but overall, you can see it's almost all ending up like right in the thyroid, right around the same area within a millimeter. So that's interesting. And then I can't remember if there's one more I want to show. I think that'll be all for that one. So yeah, that's trim, free download if you guys want to mess around with it. Pretty fun. There's another one, too, for dose calculations that you can do for radionuclides. Does anyone have a nuclide that they want to see irradiate someone? If not, I can just go with some plutonium. Go some plutonium 239, the good stuff. We can see our energies, our yields. Go to an adult male. Let's say you ate some plutonium, and it ends up in your stomach. So let's go with that kind of activity. We'll do 10 curies for 3 days. That ends up in there. Obviously, not a very good situation, but why do you keep deleting all my stuff? But we can kind of see from our phantom what kind of radiation that we can be getting from this stuff. So we can sit here and run our histories. Let's go ahead and run 1,000,000. So this is only the photons. It's not for alpha or beta, but it kind of runs it 1,000,000 times so we can get an idea of what kind of dosage that we'd be getting in our different areas of the body, like your bone marrow. And we get our total effective dose down here in sieverts. And this is averaged from all of the runs that we're doing. Like I said, we're doing a million runs. You also change like your slices, seeing a little differently like how it's going to be affecting you and where it's going to be ending up. Like you see some of it ending up here. Most of it's just ending up around there. But that's a fun thing to mess around on if you guys would be interested in anything like that. And I think that's all I had for you guys. I had a few questions for you guys, just see if you remembered. Would you rather have an acute or a chronic dose? If I were to give you some radiation, what kind would you want to deal with? Chronic, yes. Yeah, acute, it's not fun. You don't have as much time to kill those cells and deal with the consequences of that. If you have a chronic dose, like your body can keep up a lot better. So dosage really depends on that too. Like another thing I kind of want to tell you guys too is if you're hearing about these radiation amounts people get, you need to find out, is that an acute dose? Is that an internal dose? Is that, what do they mean by that? By just saying, oh, there was 3 curies of radiation. Okay, that doesn't mean anything to me. Um, there's a lot of stuff that goes into how dangerous something can be. That could be completely harmless to you if you're just a few meters away from it and not dealing with it. So next question: would you rather ingest an alpha emitter or a gamma emitter? So if I force fed you a radionuclide, would you rather that thing be launching off gammas or alphas into you? Yeah, gammas. Yeah, you don't want to end up like our good old Russian defect spy, where you have your stomach lining annihilated and can't absorb nutrients. But gammas doesn't make a big difference if it's inside or outside of you. It's just gonna launch right through you anyways. But an alpha, if it's outside of you, your skin's gonna stop it. It's not gonna be doing nearly as much. So yeah, I would definitely go with the gamma emitter. And then, what principle of Alara do you guys think is easiest to practice? And this isn't a there's no right answer here. I give my opinion on it on distance, but obviously you can change time, you can change shielding. Uh, yeah, you guys agree distance. I think so too. I think that inverse square law is really something, helps a lot with your exposure. I mean, like I said, just that difference of less than 2 meters on that one source is the difference between it not affecting you and killing you in a couple hours. So I would definitely go with the distance. Always try to keep as far away from a source as you can. So yeah, do you guys have any questions for me over any? And if you guys want to see any other stuff, I try to make this a little well-rounded of introductory and a little more advanced. So if there's anything else you guys like to see, let me know. I can give you sources or kind of go over it real quick. But I don't know. It's just kind of hard balancing because I know some of you guys know like quite a bit about radiation, and some of the others are still in like high school, haven't gotten that much into it. So I try to kind of round it out. But yeah, I am recording. Uh, I will upload that after this. Yeah, no problem. I get it. It's early on a Sunday. No one wants to be up. Feel bad for the host because gotta. I say it was like 8 a.m. your time. Never just started. early, or getting on to 9 a.m., but still. No, 8 a.m., yeah. Early. Alright, well, yeah, I just got some sources here, so that's all I had for you guys. I hope there was at least something interesting in this. Yeah, no problem. Like I said, if you guys want to download SRIM, besides the very horrible looking interface, it is fun to mess around on. You can always change, you know, I wouldn't change over here. It's what you're made out of, but you can change like what you're launching at, different things, and it's fun to see these cascades. Some of them get really, really kind of crazy. Like this is uranium and beryllium, gold and silicon, and yeah, it gets a little crazy in there. It's also on the angstrom scale. An angstrom is 10 to the negative 10th meters, so very, very small. But yeah, we can see, I mean, we have beryllium, gold, silicon, so it's ending up in these different ranges and just forming art, I guess. So I think it's a really cool software. Yeah, so if there's nothing else, I'll go ahead and stop the stream.